So you've been learning in this module about different forms of quadratic functions: standard form, factored form, vertex form, and hopefully there's been a little bit of hint as to why we might want different kinds of forms in order to communicate or emphasize different features of a particular context that we're modeling. So I hope in this video, when we actually have a real life context, you can put this all to practice and understand better why we have the different forms. So in this case, found from popular mechanics, we have a table showing data that has the batted ball speed for various bat weights in ounces. So I'm going to use W for weight and S for speed for my variable names. And the bat weight in ounces is increasing by 5 ounces at a time. And the batted ball speed for that weight of bat is as shown. And notice, just as a quick rundown here, as the bat gets heavier, the speed at which the ball leaves the bat gets greater: 68 to 72 to 76 to 78. But notice that the jumps get less and less. There's not a constant rate of change here. Now I'm just ballparking this here: 68 to 72, that's an increase of about 4 miles per hour. And then another about 4, but then it's about 2, then it's like not even 1. But then look at here. When the bat weight gets on the heavier side, we actually get a decrease in the batted ball speed and a decrease in the batted ball speed. Maybe it's the fact that the bat now is so heavy that it can't be swung appropriately quickly to get the batted ball speed that we want. But over here, the heavier the bat might actually improve batted ball speed. But too much is not a good thing. And maybe there's an optimum. Maybe there's a best bat weight to produce the fastest ball speed. All right, so let's get into this. The first thing I would like you to do is, and you can pause the video and do this, please, but generate the quadratic model in standard form. Work hard to get the initial batted ball speed, get the initial rate of change, get the change in the rate of change, the second differences as we call it, and then use all of that to build your quadratic model. Pause the video, give it a shot, and then come back and see how you're doing. All right, hopefully you've given it a shot. I'm now going to give it a shot. So here's what I would say first. Notice here that there's an initial, for a bat weight of 20 ounces anyway, there's an initial batted ball speed of 68.12. So I'm going to use this as a reference. I'm going to use a bat weight of 20 ounces, so W equals 20, and a batted ball speed of 68.12, so S equals 68.12. I'm going to use this as my reference, as my initial value. Okay, now, what about the initial rate of change? Notice the ball speed went up from 68.12 to 72.75. So you could subtract those two numbers to find out the increase. So 72.75 minus 68.12 is 4.63. So the batted ball speed increased by 4.63 miles per hour when the bat weight went up by 5 ounces. Now that's by 5 ounces. You know, we've had this chat now about how we typically report rates of change not per 5. We wouldn't say it's 4.63 miles per hour per 5 additional ounces of bat weight. We would scale that to be just per 1. So divide by 5 and just scale it down to a 1 ounce at a time. So if you took your 4.63 and divided it by 5, you get 0.926. So we're going to use that 0.926 as the initial speed. So here's what it would look like. I say create that initial linear function. That's what you're seeing here. Now, there's all the computations. I subtracted to see how much faster the ball left the bat when the bat weight increased by 5 ounces. So I subtracted to get that 4 point whatever it was. But then notice you get to divide by 5, so we scale it to be for every 1 ounce. So 0.92, so this computes to 0.926 miles per hour for every 1 ounce of bat speed. But remember I said the reference point? The reference point, going back to that linear work you did earlier, the reference point was 20 ounces and 68.12 miles per hour. So we have to do x minus 20. Now why? Watch this. When x is 20, 20 minus 20 is 0. 0 of those rates of change would all be 0. You'd be left with the 68.12, which is exactly what I want. That is, when x is 20, I want an output of 68.12. Without that x minus 20 there, I wouldn't get the right output for an input of w equals 20. And so here it is down here. Sorry, my taskbar is in the way. But so S equals 68.12 plus, there's the 0.926 from computing that. And I'm going to use the variables I use, W for weight, bat weight minus 20. All right, so there's that initial linear function. Let me just back up a little bit. So initially, and look how nice it fits. Initially, we see that rate of change of whatever it was, 4 point something per 5 ounces of bat weight, nice linear function. All right, but that rate of change doesn't persist. That rate of change, it looks to me like it gets less and less and less. In fact, it gets so much less that that rate of change eventually turns negative. And we see our slowing of the batted ball speed. And so we get our, we say, concave down parabola. So let's continue our process to find that quadratic term. Here's how we do it. So just for my sake of my PowerPoint, I dumped everything into a spreadsheet. So there's the original weights, there's the original speeds, and then here's the change, delta, the change in S. So remember that initial 4.63? And we divided it by 5 to get 0.926. Well, let's do that all the way down. So the change from here to here, 4.63. The change from here to here, 3.35. The change from here to here, 2.06. The change from here to here. Now look, the change from here to here is actually negative because the spatted ball speed decreases. And then the difference from here to here is also negative because the batted ball speed decreases. But remember, these numbers are all per 5, an increase of 5 ounces of bat weight. So we had to take each one of those, and I call that a ratio, take each one of those and divide by 5. So this divided by 5, this divided by 5, this divided by 5, all the way down to get those rates of change. Not constant. These are not constant rates of change, obviously. But now, when you look at how these changes change, notice I've called it delta delta, the change and the change in S, the second changes. If you look at those changes from here to here, here to here, here to here, they're all decreasing. Hey, they're all decreasing from 4.6 to 3.3. That's a decrease of 1.28. And then a decrease of 1.29. And then a decrease of 1.28. And a decrease. And look, pretty dang constant. It's not perfect. Not all models are perfect, but it's pretty dang constant. But just so you know, I wanted to not do it per 5. I wanted to do it per 1. So we have to divide by 5 again. So when you divide by 5 again, I took it back to here. I looked at these ratios since I wanted to be per 1. So I took those ratios divided by 5. I took this difference and divided by 5 to get the ratio. I took this difference divided by 5 to get the ratio. This difference divided by 5 to get the ratio. This difference divided by 5, etc. And look, all pretty consistent. Now remember this? In the quadratic model, that second difference ratio over there, the 0.051, manifests itself as half. And I'll just, not to go through all the gory details again, but it all came from finding the average. Now, back when we did it with the bowling ball off the dam, it was the average speed of the bowling ball. Now it would be the average of the ratios of the second differences. So you start with the first one, which was 0. You won't go to the last one, which is whatever, and you divide by 2 to get the average. Divide by 2 to get the average. So we take half of those. And so I guess I had some arrows there to point out everything I just said. But now we're going to add that quadratic term. So there's that initial linear stuff starting at 68.12. Starting meaning referencing 20-ounce bats. So we have to do the minus 20. And then half of. Now, what I decided to do here for the sake of this, I went with 0.052. I don't really remember why. Maybe because half of that was easier to compute. I don't know. But I went with the 0.052 as my difference. But I need half of it times, again, referencing W minus 20 squared. So there's my squared term. There's my quadratic term. So linear term, add the quadratic term. Half that common second difference. And then W minus 20 is my reference squared. All right, so there. Now, you certainly could distribute, multiply half, and you could do some things to make this look pretty. I'm just not going to. I don't need to. I'm going to call this standard form. I'm going to call it standard form with a reference point of 20 ounces for a bat weight and a 68.12 batted ball speed. And it's perfectly awesome to do that in this context, since that's what the context is. All right, so there it is. So I can graph it. And let's just suppose that we want factored form. So what you've learned about factored form is this. Because it's 2025, we can graph this thing. Type this into Desmos exactly as you see it. And it produces this graph, and it boom, boom. If you just tap, if you have a touch screen, or click, if you're on a mouse computer, click on those zeros, and you'll find out that there's two places where this parabola has a zero. Now, they're not always going to be practical. Remember, we're talking about a real life thing here. We're talking about a baseball bat that has a weight of something. And we're talking about the speed at which the ball leaves the bat, which is going to be a something. And so we are going to look at this just in the practical values of bat weights that make sense. We're not going to look beyond that, or we're not going to look before that. But still, for mathematical purposes, we're going to look at the whole thing so that we can get the forms that we want. And here's the first form, factored form. So the first factor is going to be found by looking at this zero. So if you input a negative 16.4, you output a 0. If you input a 92, you output a 0. And so my factors are this. Now, that leading coefficient, or the quadratic coefficient, still is there. Negative 1/2 times 0.052, half of those second differences, which were negative. But then now the factored form, W minus 92. Remember this? If W is 92, 92 minus 92 is what makes the 0. So we need W minus 92 to get to that 0. Or W plus 16.4. Why? Because it's when the W, mathematically speaking, when W is negative 16.4, you add 16.4, you'll get 0, making this whole quantity 0. And so there it is in factored form. So we've got standard form with a reference of 2068.12. We've got now factored form. What about vertex form? So again, vertex form would be graph the original function that you found in standard form, tap on it, click on it, you'll find the vertex. And now what we want to do is kind of referencing the basic parabola of 0, 0. We now have to shift to the right 37.8 units, and then up 76.4 units. And so, there we go. So still with that same leading coefficient, that can't change, but now W minus 37.8. Now why minus again? This is where it's like counterintuitive, because you see a positive 37.8 there and you feel weird putting a minus 37.8 there, but here's why. When W, remember this is your W, your weighted bat weights. When W is 37.8, 37.8 minus 37.8 is 0. So that zeroes out this whole term. And then 0 plus 76.4, bam, gives you right up there to 76.4, just like you want. So yeah, it's W minus 37.8. And there it is in factored form. sorry, in vertex form. So we've got it all now. We've got standard form with a reference. We've got factored form, two factors of two zeros of 92 and negative 16.4. And we've got vertex form with a vertex of 37.8, 76.4. Beautiful. I want to pause there for just a minute, let you get your breath on this thing, take a deep breath and think through all that just happened here. But then I have one more thing to wrap it up.